All right, but before we can understand the chemistry that occurs inside of a battery, we're going to take a look just at these oxidation reduction reactions. I mean, that is in essence what's going on here. But just to kind of remind us, so this is actually a reaction that you may have done in the lab. It works pretty well. So it turns out that if you take a solid piece of zinc, right, just solid zinc, and you dip it into a solution of copper sulfate. Let me not use red. So here's zinc, solid, and then copper 2 sulfate. The thing that's actually going to be participating in the reaction here are these copper ions. Okay. What you'll see is this oxidation reduction reaction where the zinc and the copper ion turn into a zinc ion and copper, right? And so we discussed these types of reactions at length last class. We talked about how to calculate oxidation number, and we should be able to see that since the copper is going from copper 2+ to neutral copper, it's gaining 2 electrons. And since the zinc is going from being neutral to then having a +2 charge, it has to be losing those 2 electrons, right? Because electrons are negatively charged and its charge is going up. All right. So if we take a look at what's happening in solution here, this is a little bit easier to wrap your head around than what's happening inside a battery, in the sense that you have this zinc strip dipped into this solution of copper. So you actually have collisions between these zinc atoms and these copper ions, right? And so we've talked about collision theory before and how that's how chemical reactions happen. If you remember back last class, and our last chapter when we were talking about rate laws, we talked about how even the orientation of those collisions can be a big deal, right? So what happens is if we zoom in on the molecular level here, we have this strip of zinc. So there's this highly ordered array of zinc atoms, and you have a copper atom coming and colliding with that zinc atom. And then there's this transfer of electrons that occurs, right? So again, the zinc is giving up its electrons. Those copper ions are accepting those electrons. So what you would see if you dipped this zinc strip into this solution of copper sulfate is you'd actually see a bunch of copper starting to form on the outside of that zinc strip, right? Because again, we have those copper atoms accepting those electrons, okay? The zinc is becoming an ion and floating around in solution. But so all these little crusties that you see forming here, these are our solid copper atoms that are forming. All right, so again, oxidation reduction reactions, we have this transfer of electrons. We can have an oxidation reduction reaction between copper ions and zinc, where the copper ions accept electrons and the zinc atoms lose electrons because the copper and the zinc are colliding. And so the copper is stealing those electrons away from that zinc. Okay. So you may have done a reaction similar to this in the lab. It works pretty well. It's pretty cool. You can actually see, because copper ions are blue colored, you can actually see not only that the strip, you begin to form this solid copper precipitate on there, but actually you lose your blue color as well as those copper ions are being pulled out of solution. Okay. So again, we talked about these oxidation reduction reactions. Last class, we had the skill of being able to calculate oxidation number to figure out what's gaining electrons, which would be reduction, or what's losing electrons, which would be oxidation. We even learned how to balance these chemical equations because, there's some stuff missing here. And we had this whole big, long, drawn out process for that. Okay, so just to remind everybody. So that was last class. So again, we're going to sort of now build up to being able to understand this battery. So if we take a look at a battery here, let's first, just before we talk about any chemistry, let's talk about our components here. All right, so now what we have is a solid piece of zinc. Okay, and it is in a solution. So, right, basically you have these two metal bars that are attached by this wire. And these two metal bars are dipped into a solution. Okay, so just focusing on this side here real quick. And we'll talk about each one of these components. So I know that at first it's like, wow, that thing looks kind of complicated, but let's just talk about each of these components. So over here, we have this solid bar of zinc, and it's sitting in a solution of zinc nitrate. Okay, that is connected by a wire to now a solid piece of copper, which is sitting there dipped in a copper nitrate solution. All right. And the reason why nitrate is used is because nitrate is always extremely soluble, right? So although this says a zinc nitrate solution, because we know that nitrates are always extremely soluble, we can just say that this is a solution of zinc 2+ ions. And same thing with our copper. This is going to be a solution of copper 2 ions. All right, so again, this is a pretty complicated diagram. We're gonna take this piece by piece, but for right now, all you should be able to see is that you have this chunk of zinc metal dipped in a solution of zinc ions. That's connected through a wire to this chunk of copper metal that's dipped in a solution of copper ions. Okay. What we're gonna see is just like in our reaction that we would be able to see when we put these two together in the same solution, is that there's going to be a transfer of electrons where the zinc is losing electrons through oxidation and the copper is gaining electrons through reduction. Since the zinc is losing electrons, we call that chunk of zinc the anode. Okay. And because the copper is gaining electrons, and actually we can just say this explicitly, right? So zinc losing electrons, that makes it the anode. Copper 2 gaining electrons, that's what we call the cathode. Okay. And our electrons are then going to flow from the anode to the cathode. All right. So one of the things we talked about, these little like things that we have in our head for example, an equilibrium constant, products over reactants. When we were calculating that delta G naught, that standard free energy, it was products minus reactants. The one thing that I have in my head that I chant to myself when I'm thinking of batteries is from anode to cathode, because that's always going to be the flow of electrons from anode to cathode. Just this one little four-word sentence that if you can have stuck in your brain, it'll, kind of keep you in the right direction for this particular chapter. Okay. So again, oxidation, which is the losing of electrons, happens at the anode. Reduction, which is the gaining of electrons, happens at the cathode. All right. And what's very different about this than when we just dipped that zinc into that solution of copper ions is now there's no collisions that are occurring that lead to this transfer of electrons. But nonetheless, we have this transfer of electrons that instead occurs through this wire. Oops. Right, where these electrons are still flowing from that zinc to those copper ions. Okay, what's going to happen is the zinc is going to, again, lose its electrons, right, because it's oxidizing. And so the zinc will become the zinc 2 ion, but those electrons then go flowing all the way through that solid metal zinc, through that wire, back down to the copper electrode, where they find themselves a copper 2 ion. And they then, because they've now transferred those electrons to that copper 2 ion, you get copper atoms that will form at this cathode. Right? So in this, for this one here, you see that my anode is actually going to be losing mass as those solid zinc atoms become zinc ions and then flow into solution. Whereas my cathode is actually going to be gaining mass as those electrons flow to those copper ions and turn them into copper atoms, which will then be kind of stuck on that cathode, right? So the cathode will slowly be collecting these copper atoms, gaining mass. It'll literally grow in size. And our anode is going to be doing the exact opposite. It's going to be losing atoms to the solution, which is why it's going to be losing mass over time. Okay, so this is one reason, and we'll talk about rechargeable batteries. That's a whole different ball game. But this is one reason why many of the batteries that we experience, if you just think about the batteries in the back of your TV remote, for example, they have a set lifespan, right? That's because eventually your anode will be degraded by the process of losing this mass, and your cathode ends up gaining all that mass. But so they only have kind of like one direction that they're going to work, and they don't have an infinite lifespan. Okay, rechargeable batteries are a little bit more special of a ball game. So we'll get to those actually probably next lecture. But nonetheless, so this is what you can see, that since one is losing mass, it's eventually going to be consumed in this reaction. So this reaction isn't going to just go on indefinitely. All right, so again, just to summarize the important bits, we have solid zinc at our anode. Oxidation is occurring at the anode, which means that that zinc is losing electrons. We have solid copper at our cathode, but more important really is the copper ions in solution at that cathode, because those electrons are going to flow into that copper metal and eventually into those copper ions, where there will be a reduction reaction. Those copper ions will gain those electrons. And so that's why we say that electrons flow from anode to cathode. Let me get rid of some of my markings to make this a little bit less busy. All right, so since the electrons start at the anode and they end at the cathode, we call the anode the negative end of our battery and the cathode the positive end of our battery, because electrons are negatively charged, so they like to flow from negative to positive, right? So from anode to cathode. All right, and then the little light bulb up here is just showing you that electricity is passing through it. To be clear, by electricity, I mean electron flow, right? Electricity, that's just electrons flowing. Right, so since I have the movement of electrons through this wire, I have electricity flowing through that wire, which is why my light bulb lights up. Okay. And again, what's kind of amazing is that this transfer of electrons occurs even without that direct collision between the copper ions and the zinc metal, right? The zinc metal is over here in this solution, and the copper ions are floating over here in this solution. They never actually make physical contact with one another. Nonetheless, those copper ions are able to pull those electrons through that wire from the zinc metal, right? So my cathode, my copper ions are pulling electrons. I guess I'm from that solid zinc. But this time, instead of being directly through collisions, through those guys meeting one another, it's going to be through that wire. Okay. So this is what we call, let me see if I can make a little bit more room for myself. This is what we call an electromotive force, right? This ability to pull these electrons through that wire is what we call an electromotive force, or an EMF. All right. So the one thing that we haven't talked about with regard to this diagram is this thing in the middle here. So what the heck is this doing for me, right? So first of all, this is what we call a salt bridge. Okay, and the salt bridge actually plays a very boring role in the battery. All right, let's actually see if we can keep the diagram up there as well. So a salt bridge. All this does is keep the balance of ions in that solution. All right, so first of all, that salt bridge, let's move this down here. We'll talk a little bit more about the wire here in a second. That salt bridge keeps the balance of ions in solution. So it's filled with a soluble salt solution. So in this case, potassium nitrate. All right, and so what's the salt bridge's job? Again, it's just to keep the balance of ions in solution. What do I mean by that? Well, notice because of the reaction that's occurring at the anode, that means that the anode is gaining positively charged ions. Anode gaining positive zinc ions. So in order to keep that solution from becoming imbalanced, that salt bridge will put an extra nitrate ions, extra negatively charged nitrate ions back into that solution, right? So it's filled, this salt bridge is filled with this salt. That salt's just going to kind of stay there. But as soon as we get some zinc ions that are being deposited in this solution, all of a sudden there's this imbalance where there's too much positive charge. And so that will pull some of these negatively charged nitrate ions out in order to keep that balance. Okay. Having a separation of charges, having an abundance of positive charge without any counter ions is extremely unfavorable. So if we're going to be generating positively charged ions, we better have some negatively charged ions there to counterbalance it. And so that's what the job of the zinc is, or I'm sorry, the job of the nitrate is to just counterbalance that positively charged zinc ions. Likewise, we're going to see the exact opposite. The anode's gaining positively charged zinc ions, but the cathode is losing positively charged zinc ions. Right? And since those positively charged ions are being taken out of solution, in order to keep the balance, we need to replenish them with positively charged ions. So that's what the potassium is doing. Every time a copper-2 ion gets consumed, I'm going to need to put 2 of these positively charged potassium ions in there, just because each potassium ion has a +1 charge, copper has a +2 charge. So to keep that charge balanced, I'm going to have some positively charged potassium ions flowing into this solution as that copper 2 is being consumed, as those copper ions are being consumed. All right, so here is our diagram of our battery here. Again, this is kind of the important bit summed up. All right, we have this solid piece of zinc at our anode in a solution of zinc 2. We have this solid piece of copper at our cathode in a solution of copper 2. At our anode, there is oxidation where the zinc is losing electrons, and those electrons are flowing through our wire to our cathode, where the copper 2 ions in solution are then gaining those electrons. All right. So kind of the magical bit here again is this pull of electrons through this wire without any sort of direct collision between them. So again, the reason why I started off this lecture by showing you that strip of magnesium strip of zinc dipped in that solution of copper is because it kind of makes more sense that if a copper 2 ion is colliding with the zinc atom, that there's going to be a transfer of electrons. Okay, turns out that transfer of electrons occurs even if these two things are separated, as long as those electrons have a way to flow from the zinc to the copper solution. All right, so let's talk a little bit more about this wire here. First, we got to lay a little bit of groundwork about how, basically electricity in general kind of works, but some important concepts. So again, electricity is the flow of electrons, and this is occurring through our wire. Again, from anode to cathode. Okay. So electrons, so we're going to talk about sort of how we measure certain stuff. And yeah, this will sort of be important, especially when we pick up next lecture. Electrons, of course, have a charge associated with them. So electrons are negatively charged. Okay. So charge is an important aspect of this study of electricity. Charge is measured. Let's see how best we can organize this. In units of Coulomb. Capital C. All right, so Coulomb is our measure of charge. The electrons then flow through our wire. All right, a moving charge, such as the electrons flowing through the wire. So moving charges are what's called a current. And these are measured amps, amperes, or otherwise abbreviated as amps. Okay, capital A, again, usually don't say ampere, we say amp. Right, Coulomb is not something that is as widely known, but you've probably heard about amps before, just kind of randomly when people talk about electricity, or I don't know if you guys talk about electricity, but anyways, amps is something that's probably come up a bunch. I'm trying to think, like there are certain devices, certain speakers that are like rated with for certain amps. And again, it's just sort of a measure of how much current can flow through that particular wire, right? How many electrons flow through that particular wire. All right, and then lastly, and this is going to be a very important, the potential to move electrons, or the potential to another way of saying flow current, or just, have current, I guess, although that sounds a little weird, is what's called, this is what's measured. So potential measured in volts, V, and 1 volt is 1 joule per coulomb. Okay, so a potential is the ability to pull electrons, right? So I like in the most sort of simplistic sense, potential is the ability to pull electrons. So when you think about your 9-volt battery, that is a measure of the ability of one end of that battery to pull electrons from the other end, right? Pull electrons from the anode of that battery to the cathode of that battery, right? From the negative end to the positive end of that battery. That's what a volt is a measure of. Okay. And it's something that's kind of not as intuitive for a flow of electrons. I mean, now we're talking about something fairly complicated happening at a very microscopic level, but we can kind of make an analogy to the macroscopic level, something that we could sort of wrap our heads around very easily. Let's say that we had these 2 beakers of water here that were connected between this little spigot. And at first it's closed, and I fill this one all the way up here, and I only fill this one about halfway up. And then I open up that little spigot there. There's going to be this natural flow of water from one container to the other until they are at that same water level, right? Until they're at the same level here. So this one would have this potential, this higher potential. This end over here has a lower potential. And so that's why we have this spontaneous flow of water in this particular direction. Same thing with atoms and their electrons, it turns out. Some of these atoms, like our zinc metal, has this very high potential, and it will give up its electrons, and those electrons will spontaneously flow to the lower potential copper ions. All right, there's this spontaneous direction of flow, not unlike when we have our mechanical sort of potential here with our beakers of water. All right. Cool. So all well and good in terms of analyzing this sort of diagram right here, trying to better understand what's going on. And obviously, when you sort of take out a AA battery, it does not look anything like 2 beakers that are connected with a wire and have a salt bridge in between. But packed within that sort of small casing is kind of exactly the same setup. There's definitely some different manufacturing sort of things, certain efficiencies. We'll talk a little bit more about specific batteries, but all batteries have this kind of same basic breakdown here. All right, so the next thing we're going to be able to do is to calculate the potential within that wire, calculate the potential to move the electrons based on these two half reactions. Based on our oxidation half reaction and our reduction half reaction. Okay, we're going to be able to calculate the ability of those copper-2 ions to pull electrons through that from zinc through the wire, what we call the electromotive force. And now we know that this potential is measured in units of volts. Okay, so we should be able to calculate the voltage of our battery. All right, and so how are we going to do that? We're going to be using this table, which is going to be our constants page for this chapter here. So this is a summary of all these different half reactions, all right? And this is obviously this big, ugly table, but let's just focus for right now on our reactions that we have been looking at. This is the copper ion accepting electrons and going to solid copper. And this gives me a standard potential of 0.34. Well, we'll talk about how to use that here in a second, but just note that that's one of our reactions there. So we're going to grab that entry from our table. And then we're going to find our other half reaction. Since our other half reaction is an oxidation reaction, let's just go back here. Since this one is an oxidation reaction, what's actually listed are reduction reactions. So we're going to be looking for the reverse, meaning we're going to be looking for zinc ions plus 2 electrons going to solid zinc. That's what's going to be listed on our table. And so that would correspond to this entry here. All right, this is our reaction that we were looking at our anode, but in the reverse direction. All right, so I'm going to grab both these entries so that we can kind of see them away from this big ugly table. Let's pull them over here. All right. The other one was my zinc. Right, so those are my two entries from my constants page. And again, our reaction was that the zinc solid was going to zinc ions, and that required the losing of 2 electrons. That was oxidation. And we said oxidation occurs at the anode. And then for our reduction half reaction, which occurs at the cathode, we have our copper accepting those 2 electrons and going to being solid copper. Right, and we called these values over here, so that checks out for what we see on this portion of our table. These values we call the standard potentials. They are not unlike the standard chemical potentials that we saw in the last, well, I guess the thermodynamics chapter. We'll actually talk about how they're related to delta G in our next few lectures. Okay, but for right now, let's just focus on how we use this table here. In order to calculate the potential of this battery, this is going to equal the standard potential at the cathode minus the standard potential at the anode. Okay, so this is going to be an important equation for this chapter. Okay, this will allow us to calculate the potential of that battery. To be clear, these are measured in volts because that's how we measure potential. All right, and since we haven't done it yet, let's make this our first iClicker. You guys are going to tell me what the potential of this battery is using this table here, the fact that we know what our anode and cathode reactions are, and then using this equation here. So everybody take a minute. Take a minute to tell me what my potential of my battery is here. All right. So if we look at the standard potential at our cathode, that would be corresponding to our reaction of the copper. Whoops. Cathode, our reaction of the copper. So that's this value here. So 0.34. And then we're going to subtract the standard potential at our anode, which is this reaction of our zinc here. So that's going to subtract off of that value. So I'm going to subtract negative 0.76. So what I will find is that my potential of my cell is 1.1, if I'm being good on sig fig 0. And again, the units are volts. All right. Standard, or yeah. These potentials here, if they are greater than 0, that indicates a spontaneous reaction, meaning that your battery will actually work in the direction that you intended it to, right? So the fact that we got this positive value for our standard EMF here indicates that this is the battery will work as we expect it to, right? Meaning that everything will flow from the anode to the cathode. If we got a negative standard EMF, a negative E naught of our cell, that would indicate that actually our battery is going to work in the reverse direction than what we expected it to. Okay, so we're looking for positive potentials here. And just to be clear, why is this thing called a cell? I've been calling it a battery. This is the sort of formal name for this type of device here would be a voltaic cell. Also called, I don't remember how to spell it, galvanic. Galvanic. I might have spelled that wrong, but anyway, same idea. These are actually equivalent with one another. All right, but that's just kind of the specific type of battery. And that's what we can measure our potential for. right? So given that this is the setup of our battery here, we can use our constants page to figure out which direction this battery will actually flow. Okay. Let me just actually make some notes here. Get rid of this. We have a way of like summarizing the reactions that are occurring at our battery, which is called electrochemical cell notation. All right, and so this is just a brief way of summarizing what's occurring here. So for this one, I'm going to just show you what it is, and then we'll talk about how I got this. So the first thing in our cell notation here is our anode material, which in that case was our copper, our solid zinc. The second thing, and then we separate that by a bar, and we put our anode solution in that next slot. We separate the anode and the cathode by those double lines. And then we list our cathode solution, followed by our cathode material. Right, so this right here is just a way of summarizing what's going on in your particular battery, right? Same way of summarizing this information here, just kind of packaging that into something that's a little bit more convenient. All right, so now let's just try to practice what we learned about using our constants page here by taking a look at another battery. All right, because zinc and copper aren't the only thing that we can use. As we saw from that big table, you can sort of switch up what your anode and cathode are. Different materials will lead to different potentials. All right, so let's just make note of our oxidation reaction and our reduction reaction here. Again, the oxidation is occurring at the anode and our reduction is occurring at the cathode. So just make note of our half reactions here so we can look these up. And what we're going to use is the fact that our standard potential of our cell is going to be equal to the standard potential at the cathode minus the standard potential at the anode. All right, so I'm going to give you a minute to copy down these equations because then I'm going to turn to my constants page and I want you guys to look up all the relevant information that you would need in order to calculate the standard potential of that cell. That's one big skill we're going to need to know for this particular chapter, not unlike being able to calculate our standard free energy or our standard enthalpy or any of that jazz, right? So similar sort of process here. So again, I'm going to give you a minute to make note of these half reactions here. And then I'll pull up that constants page. All right, I'll give you a hint. One's at the bottom, one's at the bottom, one's at the top. So see if you can't find our half reactions. Oh, and then when you do get it, enter it in as our iClicker. All right, so this is my first half reaction here. All right, and you just got to be careful. I mean, there was a reason why I made a point to say, like, copy down that half reaction. It's because there's a bunch of MNOs, right? And you got to pay attention to your specific one. How many electrons are actually being transferred? Ours was this one here with the 5 electrons. That's why I grabbed this entry from the table. And same thing with our iron. There's a bunch of different irons going on over here. So I need to make sure to grab the proper half reaction. That would be this one here. Okay. And then when I do my math, I'm going to make sure to take the cathode value. So that's that 1.15, or sorry, 1.51. And I'm going to subtract off that negative value from my anode, 0.45. And what I would get is my potential is that 1.96. And importantly, the units here are volts. All right, so this is actually even a better battery than the other one that we just saw, than our zinc copper one, in terms of the strength of that that potential, right? Higher volts. If we're going to do our battery notation here, our electrochemical cell notation here for this particular battery, it kind of starts out just as normal, where we're going to do the material at the anode, and then the solution that that anode is in. But then what makes this battery a little bit unique is if we look at our half reaction here, let's actually move this just so it's not too busy. You have your reactants in solution. All right, but after you have that transfer of electrons, you don't produce solid manganese, you just produce the manganese 2 ion. So both of these are in solution at all times. So the actual cathode material that you use is this inert platinum cathode. That will allow for the transfer of electrons, but won't actually change the chemistry of that cathode, right? Previously, we had the cathode growing in mass as it was accepting those copper atoms. your platinum cathode isn't going to change its composition, its chemical composition. It's literally just there to help transfer electrons. It is inert, meaning it's not reactive. So in this case, our cathode material, let me actually move, oh, that's not going to work. I'm not going to be able to do that without moving everything. So let me just start over down here real quick. Our solution for our cathode actually contains all of these here, and we're going to include that acid as well. So you would list everything in that solution, separated by commas. And then the material that makes up our our cathode is that solid platinum. All right. The only thing is I lied. You don't have to worry about the balancing here. So you would just list it as H. You don't have to list it as 8H. All right, so that's how I would do my electrochemical cell notation here, because again, if we're going to break this apart for these components, we said that that first box was the material at the anode. Oops. Anode material, which in this case was that solid iron. The anode solution, which was those iron ions. But now our cathode solution actually contains both the products and the reactants of this reduction reaction. And our cathode material is that inert platinum, right? So in some of these reactions on our table, you have a solid being oxidized, or the reduction where the product is a solid, as we saw in our last example. But it could also be, for many of those entries on the table, both your product and your reactant of that particular half reaction are aqueous. And in that case, you would just use some inert metal as your cathode, not unlike your wire, which isn't really participating in the chemistry at all, right? So same sort of idea. It's just used to help transport electrons.